So welcome to another thrilling installment. This time we're going to look at how we might create some shafts. So we're not going to actually export the models out of Inventor. We're just going to create some shafts so that we can evaluate the ideal diameters based on the load carrying that's required from our earlier calculations. So let's have a look at the information that we've got so far from in our Excel spreadsheet. The information that we've got is on a gear and a pinion. So the gear has 29 teeth, the pinion has 17. We've got the face widths, the module, center distance, DA, which is the overall diameter, the outside diameter, the root diameter, and in the middle here this is the pitch diameter, the pitch circle diameter. They're grade 6 gears and they have a radial force, so it's a force pushing each other apart, of 171.215 newtons, so call it 172, and we have a torque of approximately 12 newton meters on the gear and 7 newton meters on the pinion. So basically, if I bring up my sketch, which I carefully crafted with the highest level of skill, here's my input from an external machine of some kind. So it could be an electric motor or someone with really fast hands spinning this really powerfully, which is unlikely at 2,500 watts. So it's an electric motor shoved on the end of here, rotating this gear through this shaft on these bearings. And then the output side, this is on our overhung bearing support, which is the part that I've supplied you with 2 bearings in it and a shaft running through it, and the output on here. Now you'll probably notice I've drawn steps along the shaft. That's so that when you assemble the bearings onto the shaft, the bearings will press on with an interference fit until they come up to this face, and this bearing here will press on until it comes up to this face. So the segment where the gear is a larger diameter than the segment where the bearings are. So that's maybe 2 millimeters larger in diameter, could be 4 millimeters larger in diameter, it's up to you. And you'll notice that the input stub is a slightly smaller diameter than the bearing stub. That's so that the bearing doesn't have to press on all the way along there, but just the last bit. Okay, so that's fairly simple stuff. And the diameters of these bearing stubs, you want them to be the same diameter that you will find on a normal bearing. So bearings are typically 10, 12, 15, I've got it here somewhere, 10, 12, 15, 20, and I think 17. Yeah, 17. So 12, 15, 17 and 20 mil diameter are the typical diameters that you'd have on the internal diameter of a bearing. Okay, so in our case, you know, you were looking at 12 or 15, probably maybe 17 on these bearing diameters, depending on the loading that you've got in your gearbox. Everybody's gearbox will be different. On the output, these are specific bearings to go into the stub that we've got here. Now the stub that we've got here, this overhung bearing housing actually has, it's actually flanged, so it's got a recess there, and the bearings themselves on this end are designed to be flanged, and it does say that on Brightspace that that's what you need to look for. So you will identify the inside diameter, the outside diameter of the bearings based on the inside diameter of that model that I've given you. And then you'll select a flanged bearing, and I'll show you how to do that in probably in the next video. and match it with and then you can either have like a 12 or a 15 mil diameter on this, the insides of these bearings here. Okay, so you could have them stepped and maybe have a slightly different diameter here and here, but I would go with a single diameter along here, and then you'll press the bearings into it. And whether you have this stub where the gear larger or smaller than the stub where the bearing is up to you. But the bearings here, the portions here, need to be either 12 or 15, and they could be 12 and 15. It's up to you. I would go with the 15 here and the 12 there if I was having two different diameters rather than the other way around. But either way, you want the diameters here on these bearings are either going to be 12 or 15, depending on the bearings that you select. And then this diameter coming out here needs to be less than whatever the diameter is here. That will then make it easier to press the bearings onto the shaft. Hopefully that makes sense. And I would typically make this portion slightly larger than this, so that when you press the bearings on, they go on up to this face for the first bearing. And then the second bearing you'll press on until it's the right depth. And you could put a sleeve here between the two, so I could maybe colour that in a slightly different shade, just to show you where it might go. So you might put a sleeve, a cylindrical sleeve, just in here, so when you press those two bearings on there, they won't go too close. They'll be kept the right distance apart for when the whole thing is assembled, and that will then stop everything being out of position. Right, so that's a quick overview of the type of thing that we need to do. So let's have a go at creating this top shaft here first of all, and then we'll maybe look at this shaft as well. So we're back into Autodesk Inventor, and I've already got an assembly file saved. I've made sure it's metric, and I'm going to go with, not with spur gears, of course not, shafts. Here we go. So it may or may not look like that. And there's a model view there, so you've got an idea of what it's going to look like. But let's concentrate on building the model here. Now, if we go back to our initial sketch, we're going to need, let's say, 30 millimeters stuck out the end, and then the width of a bearing, let's say 12 for now. We can always adjust it later, but this is fine for getting a calculation done and seeing that you've got roughly the right sizes. So we'll go with maybe 12 long with a 15 mil diameter, maybe make this 14 mil diameter and 40 mil long. My gear is 28 mil, so I'm going to make this 30 mil long, and it needs to be up from the size of that. If that's 15 mil diameter, I'm going to need 17 or 19 mil diameter there. I can then drop down to another 15 mil diameter here for the bearing, and maybe make that 12 mil long, and that should do. So let's build my shaft. So at the moment you may have this all set up slightly differently, so make sure you're using sections. There we go, and this dictates our section, so it tells you what's it like at the beginning. So you could have a chamfer, a fillet or whatever. We don't really need that for this stage. We just need no feature, so we're not going to worry about a feature on the end. Then the cylindrical portion. Is it cylindrical, conical or a polygon? We want a cylinder. Are there any features as it comes off the end? We don't want any features as it comes off the end of that portion. This next one says, is there anything on that section of shaft that you want to add in? You could have a keyway groove, retaining ring, a wrench flat so you can put a spanner on there, whatever. Okay, don't need any of that at this stage. So that's going to be the input for my shaft. I then need to say, okay, what's the sizes on this? I'm going to go with a 14mm diameter shaft section, and I'm going to make that 30mm long. That way I can drive with my motor onto the end of that shaft. I now need to add the next section. So there's my first section here. So let's add another section to the shaft. So here we go, insert cylinder, and it drops down underneath, and then I can modify that section. So this one needs to be 15 to support it on a bearing, and I'm going to make that 12mm long. There we go, 12mm. So this is 15 by 12, and there it is, 15 by 12, the next section. Now we need the section that's going to carry the gear. So I'm going to make that 17 by 30. So it's just wider than the gear. That way the gear won't start machining away at the inside of my gearbox. Okay, you don't want the teeth rubbing up against the inside face of the gearbox, so hopefully that will prevent that. And then we need the bearing on the end. So we've got 3 parts of the shaft so far. Let's put the next portion in. So another cylindrical feature, and this one is going to be 15 by 12. So 15 by 12. So this is just our starting point. Sometimes we like to put a different size bearing at each end, so that you can't put the shaft in backwards. Okay, so that's quite a useful thing, but sometimes we just want one pile of bearings all the same. So there's, you know, advantages and disadvantages to both ways of doing things, and it's up to you to decide, you know, what's appropriate for you. So let's go to our calculation. At the moment we've got, let me just delete all of these out. There we go. First thing we want to set up is our supports. So where is it supported? We've got a fixed support and a free support. We're going to put our fixed support, that's this one, we're going to drag it into the center of where our back bearing is. We can then have our free support dragged into the center of where our other bearing is. So there you go. So there's our 2 bearings done. 1 bearing, 2 bearings. So they're supporting it here and here. Now we can set up some loads. Our loads are going to be our input torque. So let's set up our input torque. The value of our torque on our input is, let's have a quick check on our Excel spreadsheet. As you can see, 12 Newton meters. We've also got a radial force of 171.215, so we'll look at that in a minute as well. So 12 Newton meters. There we go. And then we can just drag that into the center of the gear section. No, we're going to send it, we're going to drag it up to the end, near the end of the input section. So that's our input torque. And our input torque is going to be the same as our output torque. So we need to add another torque. So here we go, add torque. Here we go. And it'll automatically set it to the equal and opposite of the other torque. If you go and modify the values, you'll then have to modify, if I go in and modify the value of this torque, I'll have to redo this one. Okay, but whatever that is, this one will be minus the value of the other torque, obviously. Now we need our radial force. So this is the force of the gears pushing each other apart. So it's a load and we've got a force. Add radial force. And our radial force value is, for me, it's 171.215. So 172 sounds close enough. So we've got 172 newtons. Click OK, and then I'm going to drag it into place. And it needs to go right where, in the center of that section where the shaft is. There we go. Where the gear goes. So that's all now set up. However, we haven't chosen any material yet. Now, the material properties don't make huge amount of difference because it's all about deflection, really. And Young's modulus, if we think about Young's modulus on steel, most steels have pretty much the same value. Okay, obviously if you can make it out of malleable cast iron, that's great because it's cheaper. So let's try malleable cast iron. Here we go, and we'll hit calculate, and it's calculated and nothing has gone red. That's passing our test. And let's have a look, see how much stress we've got in anything. So we've only got the maximum reduced stress is just under 39 megapascals, which is best part of not very much. And our deflection is only 1 micron. That's hardly anything. So the deflection in there is negligible on my shaft, obviously. On your shafts it might be different, but that means I could probably get away with smaller bearings, which makes it cheaper. So I can swap this bearing here for a 12mm, maybe swap that for a 12, and we'll see if we can get that shaft diameter down. So let's change the input stub. We're going to try out some different sizes and see what works. So we'll make that 11. See if we can get away with this only being 12. So obviously we want to try to reduce the amount of material, which then reduces the amount of cost. But the main cost here is the diameter of where the gear sits. If you're machining from solid, from a blank, that's the bit that's going to make it cost the money. So we're going to drop that down to 14. Let's go to our calculation now and hit calculate. So it still passes. We're up to 2.4 microns and 79 megapascals. So that's probably pretty close to, you don't really want to go much more than that. And you've got various graphs here. Which you may or may not be interested in. We don't really need these graphs for our project. All we need is the components the right size. Okay, so at this point what you need to do is to write down all the sizes of everything on there.